especially the perspective projection. And some of idea might be told in related works, related course such as computer graphics, and some other courses related to 3D things. And so today we have actually mainly two topics. The first one is pinhole camera art, and in Chinese that is actually the 针孔摄影机 in Chinese, 针孔相机，针孔相机。Okay. However, I have to emphasize that the pinhole model here is not exactly as the 针孔相机 you heard in on news. For instance, when someone would like to pick someone else in a motel or somewhere, you may have a tiny camera, tiny hidden camera called in Chinese. This is called 针孔相机。针孔相机。However, these things actually not identical to the pinhole model we talk about. Pinhole model is actually a kind of simplified for the camera. Okay, approximation of the camera. So so we will talk about when after we talk about the pinhole camera and the camera with lens, then we'll talk about what is exactly not exactly what is the pinhole 的针孔相机 we talk about those tiny camera actually then have a small tiny lens in front of this camera. Okay, and our human eye is actually the kind of camera for human, right? So it's sort of like the camera with lenses situation. Okay, and this course we will involve some of slides, for instance, from our textbook by forces and the bonds, and also some related contents or lecture from the lecture slides from a lot of school. Okay, so we appreciate their slides and we mix and include some new contents. Okay. So before we talk about the cameras, perhaps the first thing is that how ancient people think about the 3D thing. Yeah. So let's take a look at the two pictures. This one, I guess most of you have idea who made these pictures. And right hand side, I guess some of you may have seen this one in such as Vatican City or somewhere in Europe. Okay, so the left hand side is Picasso's The Dream. That is famous. The Picasso in Chinese is Picasso, right? He's a famous Cubism artist. And the right hand side is actually an earlier work by Raphael. Raphael is the Raphael. That is the famous artist in Italians, the artist, and you may have some similar name from Ninja Turtle or some comics, right? Yeah, this is one of his masterpieces called the School of Essence. In Chinese, that is 雅典学院 or something like that. Yeah, and this is around the time of 40th century. Yeah, that is nearly 600 years ago. And when you take a look at these two kind of picture, my first question is which one do you think is more realistic? So I guess most of students may choose this one. Yeah. But some of them may choose this one. If you choose this one, means you have some talent for the cubism. Right? You may want to decompose the real thing. The cubism idea is you usually decompose a real things into pieces. Yeah, just like the face and some bodies and decompose into pieces, several pieces, and then stitch them together to form some ideas the artist want to express. But I'm not an expert of painting, so my exposition may not be correct. Okay. So let's move to the right hand side, the Raphael's. Yeah. For the Raphael's paintings, in this painting, you may see that okay, this indeed a painting. It's not a photo, and this paint is actually paint on a wall in Vatican City, Vandigang, right? And however, you can see that okay, the ground look correct, yeah, the doorway look correct. However, the lighting may not be perfect, right? So, and the ratio of this person look correct, right? Because the first simple idea is that okay, the frontal person, for instance, this one may have a larger size in the screen, and or on the painting, and for the person here, or person here could be. Say the famous philosopher here, and he's slightly further from the painting, so it's slightly the smaller in the sky in the painting, right? And however, during the same years, that is for Chinese, that is the Ming Dynasty, the Ming Chao here. Ming Chao is from say 30 to around 40, 60th century, right? And at the same era in Chinese, actually their paintings not so realistic, even though they can capture some idea, such as the frontal eyes is larger and the farther guy further is smaller, yeah, or a distant guy is smaller. However, the perspective or the ratio is not so correct. Uh, Perhaps there are some artists do that, did that, but for the mainstream, they did not do that. So what is the main difference? So one of the key difference is the idea of so-called vanishing point. So for instance, if we can see the center uh, the the doorway or say the archway here, and you can see like okay, our line will probably gradually to shrink, not shrink, converge to a point if then extend or intersect at a certain point. And so that is called the vanishing point. And there are a lot of whenever you observe the real world, such as this is our library in Jiao Tong campus, right? And whenever you see this one, and you can see like okay, for those lines we can say it's converge, is or intersect at some point, and even though this direction, top direction we can also do that, but the intersection point is perhaps far from the center of the painting, and we can do that on the right hand side. Yeah, as long as they are parallel lines. Okay, and so we also have this kind of intersection upward, and so this is library, right? And this is another view or another pass on the Hsinchu's campus. You can see that okay, we have a road here, and their light can whenever you extending those light, they will intersect somewhere, and even the building can intersect with this point, intersect with this point. So and let me show you another figure. I guess 90% of people or students haven't seen this one, right? Do you know where it is? Yeah. And actually, when I came to Jiao Tong University for, say, nearly 9 or 8 years, I have no idea where it is. But after I do some administrative job in the library and in the eighth floor of our library, and okay, I finally know that this is actually our history museum of NCTU. Yeah, uh, NCTU History Library Museum. Yeah, small museum. So that is at the seventh floor of our library. But actually, there are quite few person to attend it until when I do some administrative job in the international affairs office, and we have to take some international visitor to visit somewhere. So it is a good place for us to show that okay, we have some history and we made something. Yeah. So anyway, so let's go back to this slide. And so during the uh, Renaissance year, and the artists find that if you would like to draw a box here, and of course you can make them perfect parallel in the world. However, they will not so realistic because when the box is has a distance from your camera, you should not be parallel as well. So then have a trick to rent those painting. The idea is find a vanishing point, which means perhaps we can define the vanishing point here, and then we can reversely draw a lines, and we can construct, for instance, a box that is more realistic than the pure parallel version. So this is the parallel lines, parallel edges, and we use the edges that can intersect at the vanishing point. And when we rotate the box, we can see that okay, we can construct two vanishing point here, and if we further tilt our box, we can got say, so for instance, this is our library. If our camera is see in this way, and we can find uh, three vanishing point here because for box we have three set of parallel lines. For instance, we parallel these two parallel, and this one is for is parallel, and for even for upward lines then could still be parallel. So based on those parallel line, we can find three vanishing point. So there is a lot of uh, uh, painting trick, such as we can use the 3-point perspective, 2-point, 1-point perspective. That is mainly try to mimic the real world situation. Yeah. And so here is just show you some idea how the painters or artists do that. For instance, if they would like to draw a street view, yeah, street view, yeah, some city view, yeah, and perhaps then we will first find the horizon line because everything will vanish uh, to the horizon, right? Yeah. If then would like to draw a building here, perhaps then can draw a vertical line here, and then determine two vanishing point here, and then draw some lines. Yeah, then uh, for instance, based on these vantage points, then can extend those lines to this line, and then afterward, then can use their rubber to erase those points, those lines. Then they can get uh, then can get a building or a box that fits the vanishing point rule, and using the same trick, we can construct, for instance, extend line here, then draw some line box here, and say perhaps draw a line over there, and then you can draw uh, a painting. They are confront to the conform to the vanishing point rules. Yeah, and however, with this kind of restriction, we can only paint such as the a painting with full of parallel lines. For instance, this is a box, they have a parallel set. However, if you would like to capture the real scene uh, without any parallel light, uh, this kind of trick may not work well. So in that era, around 1540 to 44, there's another uh, you can say the system, or you can say a painting trick, not a trick, painting technology called camera obscura. Obscura uh, in Chinese could be 暗房, but I'm not sure whether this this translation is correct, but it is sort of like this kind of idea. So like the idea is that then OLED then can capture a real scene, and for artists to paint on the wall. So the idea is if you would like to paint this wall, for instance, if you like to paint this wall, this white wall, and your artist is have trouble to mimic or reconstruct the whole thing, right? So one idea is that perhaps we can use, say, a board or something, and you can draw a hole here. So that is our pinhole here. And if you have a strong light here, for instance, you have a super large candle here, or some bright light over there, and artists have chances to, for instance, mimic uh, the scene here. However, the scene is reverse one. Yeah, you can see. We will talk about later. The main idea is that your line is will go straight forward to project to this point, and you can go straight forward to this point. Then, so our light will go uh, straightforward and unbending unless there's some large maze or something distort, or black hole or something to distort your light. Otherwise, uh, light usually go straight light uh, along the air, on the air, in the air, right? Okay, so so this is actually one of our most earliest camera model. So the idea is using a pinhole to capture the scene. Okay, and this kind of camera actually is still applicable right now. Let's take a look at this one. So this is actually one of the homework of my daughter in elementary school. She's around 8 to 9, and last few years, there's solar uh, eclipse, right? So eclipse is 日食, right? So the teacher asks student to observe the change of the eclipse. Okay, so one of the way or their homework is they have to find a box, and they have to say on this box they have to use their pin to uh, peek or poke a hole here, just like this one. And their version is not putting their hand into the box. Their version is that they can leave a so-called observe window here, so the student can through their eye to observe the change of or variation of the solar eclipse. Right? So this is kind of a pinhole model. Okay, so uh, however, I guess some of you may may find that okay, the pinhole model is actually quite limited because then have to rely on some strong light, just like solar light, the sunlight, right? Or some even the moonlight may not always perform good on this kind of camera obscura. So, but before we talk about why we use or not use the pinhole models in different cases, let's talk about the the geometry model for the pinhole model. Yeah, I have to emphasize in advance that the model is important, and we will use the pinhole model for most of our geometry, uh, 3D scene geometry analysis. in the later chapter. Okay, so don't think about okay, it's just a chat about the pinhole model for ancient painting. It's actually a still applicable uh, model here. Okay, and about the pinhole camera here. So let's take a look at this figure here. So for instance, if we have a candle here, so this is our candle, and this is our pinhole. So so we have said that our light will go straightforward directly pass through the pinhole and then can reach our board here. So this board we called image plane. That is that is the plane for image to image. Image means to appear, right? And so light will go straight forward. Okay. So for instance, you can see the tip of the frame here will appear here, and the bottom of the frame will be here. Okay, so the first idea is that okay, the image generated or the exposed in this kind of pinhole model is upside down. Okay, so but usually in the later course or in some related course such as computer graphics, we usually move our virtual camera to a virtual image to the right hand side, this side. So why do we do that? The first idea is that because if you want to draw this kind of or analysis your scene, if you have this kind of box here, you will use additional space. So we usually map this one to here, and because we keep the distance the same. For instance, this distance we call it d, and we keep the same distance d here, and we can see that okay, the the candle here is actually identical to the projected one, but just downside up here, just reverse one, and this virtual camera or this mirrored plane or reflected uh, the not reflecting the symmetry the uh, symmetric plane here is actually a smaller version of the candle, right? So there's the tip is up and the bottom of the candle is down. Okay, so this version is actually easier for us to analysis and to paint. So we usually use a virtual image here. And for computer graphics, this camera have also another meaning. That means as if you are this is your eye here, and the virtual image could be sort of the screen, right here. And in most of our course we will move our image plane to here. Okay, so this I guess a lot of students have learned graphics have know that, but uh, just that some other students know that if you haven't taken the graphics course. Okay, so so the idea is that this is some figure from a graphics course. So the idea of camera is if this is a pinhole camera here, and we have a film here, and if you would like to capture this kind of this temple here, holy temple here, and whenever light go straightforward to through the pinhole, you can visualize that in your film. And uh, if you put a virtual uh, plane here and record every passing light, you will see that okay, uh, it's just like uh, the the film, the image appears on the film. Yeah. So so this idea is called perspective projection. Perspective in Chinese is called 透视图. So the advantage of perspective projection is that it can say they can tell or they can represent the so-called perspective idea. Perspective idea is that such as vanishing point. If your lines go straight forward, you through the perspective projections, you can find the vanishing point in this light. For instance, if you have a tiled box here, and we can get the vanishing points at certain places. Yeah, we will have some other figures later. Okay, so the pinhole model is and the perspective projection is one of the most a common way or a common tool for us to analyze the 3D scene. Yeah. So let's use a simple equation to formulate the projection or the perspective projection. So if you have a point here, that is a P here. So this P is not restricted to a single point. It can be any 3D thing. For instance, if you have a tree here, every tree could be a P, but just P1, P2 here. And every point in a 3D scene, you can use the perspective projection to form their how they look like in your camera. Yeah. So we first simplify to a single P here. So if you have P point P here is three-dimensional coordinate is X, Y, and Z, and whenever it goes through a pinhole here. And this one can also be regarded as the camera center. Okay. Center. Lens center. Uh, we will later see in the camera with lens. And because the ideal pinhole model is the line can only pass through the pinhole. For instance, this is a box. And our pinhole model is that uh, only the pinhole can is transparent or visible, uh, or the only area they can pass the light. Otherwise, other places are obscured or occluded. Yeah, or other lights are blocked by the box. The pinhole is the only hole or region that can pass the light. So the way of the light of this point P can only pass through the pinhole to this point P plane here. Yeah. Okay, so what is the coordinate of X, Y, and Z? So the idea is also simple. Assume that this is our distance Z here. Yeah. And so this is the projection point. For instance, if our projection points have a distance, for instance, this is a film. Film is the 底片, right? Currently, we no longer use the film, so we use perhaps the CMOS here. Your sensing, uh, your sensing unit or sensing camera sensing element. Yeah, CMOS or CCD here, and so given a line straightforward here, and you can see that because this is a straight line and this is the z-axis, and so we can see that here's the angle theta here, and there is a single theta plane here. So theta is equal to theta plane, right? So you can see that this is actually a kind of the so-called similar triangle. Means these two triangles are similar. Yeah, and their shape is identical to others. However, their size is different. Yeah. So if these two uh, triangle are similar in shape but different in size, perhaps we can use a single rule, such as in Chinese this is the 相似三角形, to find uh, the projection point. So the idea is that, for instance, the ratio here, the we what is our known? Known is the X, Y, and Z here, and we also note the F here. F sometimes we sort of similar to the 焦距 here, focal length. 焦距 here. Here's F1. Sorry. And so based on these three known value, we can estimate the p prime, the location of p prime. The idea is quite simple. For instance, if we have x versus z here, it's supposed to be they have a similar ratio by x prime and z prime. However, z prime, the film here, the z is the f prime here, so we can do a substitution. We can put f prime here, right? So whenever we move up here, so we can get x plus is equal to f plus multiplied by x divided by v here. Okay, so this is a simple projections uh, for the point P here, and through the same idea, we can get the y plan here. Okay, so the projection or prospect projection with the pinhole model is quite simple because there's only some uh, similar. You can simply use a ratio of triangle to reach or estimate the x prime, y prime, and z prime here. Okay, so so let's take a look at how perspective projection and the pinhole model can explain some things, uh, some 2D things we just mentioned about in the painting. So before we going further, we say that we have seen that perhaps we can move our camera here or image plane here. Okay. Okay. So if our image plane is at a rotation d, distance d, and we can get its symmetry location here and put the virtual camera here. So this is our virtual plane here. Sorry, not virtual camera, virtual plane. Virtual plane here, and we can because the triangle is similar, right? So for instance, this is a P, this is our P plane, right? And we can say this one is a P double plane here. So for instance, this is the D here, D here. This is the distance, so this could be the negative D here. So yeah, so we can see that if you have a candle here, candle here, say these two uh, small candle, projected candle is actually upside down, and this one is just the smaller version of the original one. So this is original. So this is the projected, right? So we can also use the same formulation x, y, z here. So we can say this double prime is f, sorry, d here, d x double prime, sorry, supposed to be d plus uh, multiplied by x divided by d dy d here, right? So we can use f or d here, right? So through this kind of uh, mirror or virtual planes, we can make our drawing or analysis simpler. Yeah. So in the this kind of projection can explain or mimic the real things, the real idea about the so-called foreshorten or uh, shorten. Yeah. The idea is for what is foreshorten means. For instance, if you have uh, for instance, some guy here, the guy closer to the camera is supposed to be larger in the image, and for farther from the camera, they will be smaller. So for shorten means the closer is larger and the more distant uh, is smaller in image. Yeah. So using this kind of perspective projection with pinhole model, we can uh, interpretations, or uh, we can interpretate this kind of things. For instance, if you have some guy standing here, and this is our plane here, image plane here. Whenever this guy move backward or move uh, uh, farther from the original places, when you project to the scene, then you can see that okay, this guy is become shorter in the camera. And if this is the door, the archway we have mentioned here, then you can see that when archway is far from the camera, archway will be uh, uh, shorter, right? So this is figured from the high-speed real-world Taiwan, and you can see that for low seat here, for the closer seat, they will be larger in image, and when they are far from the camera, they will be smaller, and then will uh, when you extended those lines, it will be say intersect at certain vanishing point, some in the camera, or out of the in the image, or out of the image. Okay. So I wonder whether there's any question about the perspective projection and the pinhole model. If you have any question, you can raise your hand through the WebEx. There's a button called raise hand raising, right, or something like that, and you press, you can text or send a message. Okay, if you have question, or you can also ask question after the class. Yeah, and so here is just another figure to let you know that if you have someone here, and these two guys have the same height, they are the same height. However, when this guy is far from the camera, for instance, this is the camera, you will see that the A is much shorter than C in the image, right? And if you have a super taller guy here, this is say 200 centimeter. For instance, this is the keys 100 centimeter here. However, if this uh, guy is say 2 tons, if the distance is 2 tons for the guy of C here, and it will look just as tall as C in the image. Their height is the same, but it actually have 2 tons taller than the guy of C. Yeah. And so how about the vanishing point? So we say we have explained the foreshorten idea. Yeah. And how about vanishing point? So let me show you a simple idea. So if we have, say, so the vanishing points mainly for the parallel lines. We have said that, for instance, if you have box, so these two lines, these lines are parallel. So parallel line will intersect, extend those parallel will intersect to some vanishing points. And how can we explain that in through the pinhole model? So let's take a look at this idea. So if we have a virtual line here, a parallel line, so these two lines are parallel to each other. For instance, this is A and B here, A and B parallel to each other, right? So assume that here is the distance here. Yeah. For instance, if you have they have a shortest distance here. So because they are parallel, so their distance will keep the same. So for instance, this is the white here, and we can see that based on our pinhole model, we have a projection here. So this is our virtual camera, right? And so we can use for instance, this is F here, and this is the distance Z here. Yeah. So the distance between these two could be, say, a ratio between, say, f and z, something like that. Yeah, but I'm not carefully draw, but say the ratio here supposed to be, say, f multiplied by w and divided by z. And whenever we increase the z, say for instance z go to somewhere with, for instance, to reach the maximum number, the infinity, right? And we can see that the, the distance on the image, for instance, this one is the distance between these 2 points. And if we move these 2 points to the pretty uh, large distance away from the camera, and we assume that they are infinite, and so their, say, their y's, the y's between two lines is still constant in 3D scene. However, for 2D scene, this is the projected things. Projected things, because the z go to the infinite, so this value will, the distance between two lines will become 0, right? So then actually reach, uh, converge to the same point, yeah, because there's no distance between these 2 points, yeah. So this is a simple uh, deduction about the vanishing point, but there are actually some more formal deduction, yeah. Okay, so uh, yeah, perhaps let's take a short break. Perhaps let's take okay, we can still take a 10 minutes break. So perhaps let's take a 10 minutes break, and then we can then go back to talk about further or different kind of projection. Okay, so take a short break.诶，有同学问说第12页在叙述什么？这是第12页吗？还是什么？因为我不确定你们的页数跟我的是不是一样的。对，刚刚问问题的同学在吗？嗯。 这一页在讲什么？这一页是在解释 vanishing point， 就简单的证明为什么会有 vanishing point 这件事情。对啊，就是说我们刚刚原来用中文讲，就是说刚只是简单的证明说，如果有一个距离是 w 在这边，所以假设这边投影的距离叫做 w plan 好了。然后呢，所以我们刚刚的证明是说，这个 w plan 呢，其实类似于 f 除以 w 除以z 好了。所以假设这个点的距离叫做 z。但是呢，如果当你的 z 走向无限远的时候，z 走向无限远的时候，在这个平行线它的间距还是 w，但是当它投影在画面上面来的时候，它的间距 w prime 已经趋近于零，所以这两个点已经交在一起了。所以这个是刚刚在讲的事情，对啊，简单的证明。但是这个 vanishing point 还有很多正式的证明吧，大概是这样。那有回答到同学的问题吗？那 vanishing point 讲的是说任意平行点，就一组平行线，其实不止啊，就是反正就是某一组平行线，最后它会交于在画面当中会交于一点。我们没有真的需要用到 vanishing point， 但是只是解释说我们日常看到的一些现象，其实可以用平衡 model 来解释，好吧？
哎，老师，请问听得到我的声音吗？
关于有同学问到说为什么需要一个 virtual plane，其实只是方便而已啊。就是说我们回到刚刚这一个图，对啊，就是平衡 model 真正的成像在这里。平衡 model 真正成像在这里，这是成像在这里。然后呢，我们放这个东西在这里，主要是因为呢，其实我们你真正要画的时候，你都要画，在分析的时候都要把你的蜡烛画到这边，而且是倒的。其实分析不方便，就像你要蜡烛还好，你一台车子你就倒着画，那就很麻烦，对不对？那所以呢，我们其实画了一个像在这边画了一个 virtual camera，它的距离假设是一样的，假设叫做 dd，这个跟左边这个只是上下相反而已 ，size 什么全部都是一样。啊，用这个分析其实比较简单，对啊。那就是而且我们就会省掉一段距离，这段可以不用画，我们就只画这一段，对啊。所以就像下面这个例子， 就是你真正要画的时候，其实你需要把它延伸，然后来画。这样其实你拉大了你的空间，分析的空间。所以我们其实比较喜欢的是画在这里，对啊。但是只要把上下颠倒，就是这个像，对啊。而这个像其实也不是那么好用，像我们在拍照的时候，对不对？假设你真的用 Pinhole Model 拍，那你在拍的时候呢，你东西画头在这里，其实是上下颠倒。那我们一般你相片真的在用的时候，你还是把它转回来转正，对，你还是要拿的你的蜡烛还是往正的比较看比较容易。那所以我们就会在这边插 virtual camera，其实只是简化我们的画法而已。OK，上下颠倒左右会相反吗？应该这么说，就是说你看你的样子，例如说假设你有一个，你把它想成是光的直线进行，对吧？就是说如果你这是上下，画个例子来讲，假设有一个旗子好了，对吧？所以这个旗子是我们画斜斜的好了，这样斜斜的。然后呢，你的旗子经过这个光的时候过去，不是经过这个点画出来，你的旗子经过，假设在这个是旗子是往 x 方向加的方向哦，你经过光的直线进行过去之后呢，它会到旗子会在下面，然后会导向另外一边，对。所以，但是呢，如果你在这个投影上面的话，其实它是会在这里哦。应该这么说，我们产生下面这一个拼后的像，它其实是上下颠倒，左右相反，对吧？然后呢，因为它是相似三角形，最主要是相似三角，相似三角形你原来长什么样，下面就是长什么样子。但是，所以你在 virtual camera 上面看到的就是一个缩小版的原物就对了，投影过的原物，就是其实就像你眼睛看到的东西一样，对啊。好， Hi, I'm back, and sorry for defer the starting of defer starting the class because there's a lot of questions. We in the during the break we have answered a few questions. The Someone asked whether we will upload our video recording. Yeah, yes, if we uh, present through the WebEx, we will record as well, and at the same time, yeah. And some other student asks, okay, so then hope that you have to explain the ratios. Yeah. For the question, perhaps we can move this one about the ratio between the pinhole distance. This is actually just the similar triangle, but we have talked in class, so let's move to the break. Okay. So I will explain if someone still have this question. We will explain after the class. Okay. Or during next break. And there's another question X about the next week. Uh, our school's original plan is go back to the normal cases. That is, we supposed to be back to uh, class in person. That means 实体上课. However, I'm not sure whether there are anything because, for instance, for this class, during the Friday or not Friday, before the starting the semester, uh, at for instance, Monday is the starting of the semester, and then told us, okay, you have to move to online on Thursday. So I'm not sure whether, but we will announce. I think we will announce before the Friday. Okay, so, uh, but I'm not so sure. Yeah, but if possible, we will try to still provide the online streaming. Yeah. Okay, so but whenever we have new updates, we will uh, announce on E3 and also on the temporary announcement course. And so perhaps let me move forward, and if you have some idea about the projections, as we can uh, discuss it during the break or after the class. Okay. Okay, so I hope that you all can see my screen, and I will start record our second class today. Okay, so in the next class, we talk about the perspective projection, and I briefly remind you some idea. Idea is say if you like to generate the estimate price, uh, also answers the question about ratio. If you like to estimate the point P here, P plan here, actually, when you take a look at these two triangles, so this is for P plan. This one is for P here, right? Because uh, we follow the lines, straightforward line, direct line rules. So these two lines are uh, uh, along the same line, right? Along the same ray. So, for instance, this is the negative z axis. So, uh, because the ray over here is identical, so for the theta here, then on the same, then have the same theta here, right? So because this is a similar triangle, right? A similar triangle idea is if you have x plane, z plane here, and this y plane, z here. So x versus z is equal to x prime z prime, right? So we can simply get x prime z prime here, and whenever you put the z prime as a f here, you can get x prime is equal to fx, for example, divided by z. So that is the ratio, right? So you can say the position p and its projection p plane here. The p plane is just shrink its size according to the z here, right? So if you have say another point p plane here, of the same height, p plane, p double plane here. Yeah. So if you like to do the projection, it will be shorter because there is their f is larger. For instance, this one is fx divided by z. However, this one is f double plane x divided by z double plane here because their z is larger. So the projecting height will be shorter. Right? So that is the main idea. Yeah. But if you have problem, we can still discuss in Chinese after the class or during a break. And so the perspective projection is a simple idea. It's a simple but quite useful idea. Yeah. It's popularly applicable in computer graphics and the computer vision field. Yeah. And in addition to uh, the the general or the common projection, there are also some terms occurred in our textbook. The first one is called the weak perspective. So it's kind of the weak or simplified version of perspective projection, but it's for me it's not really useful. Yeah, we do not really use this kind of projection. So what is a weak perspective? Its idea is that just the same uh, of the perspective projection through the pinhole model, we can still have a pinhole here. Right? So its idea is that if most of your object or your target point is on the same plane, for instance, you have say a painting here, or all of your students stand on the plane. Quite strange, right? Yeah. And for instance, or let me change another example. So for instance, if some guys here and they jump on the plane, along the plane here, so its movement here will become, say, reverse one here to here, the reverse one. You see that if we don't do the virtual plane, you have to draw everything reverse, right? Upside down. Yeah. And so for instance, this guy move from the q from p to q, and its projection from the p plane to q plane here, right? So because we have known that there is a ratio between the, the triangle, these two triangles, right? So there is what is a weak perspective, which means if your moving object is just along a plane, they keep a constant distance, say uh, uh, z0 from the camera center. So in this case, perhaps this movement, say for instance 1 meter, you can simply use a simple ratio. For instance, this is say the 2 meter here. And for instance, this is 1 meter here. Yeah. And based on the ratio, so we can simply estimate its movement or their distance is say uh, 0.5 meter, right? Just because the ratio, because our movement here is say 2 meter. This 1 meter here. So whenever you move some point on the plant, so this is so in this model, then assume that say for instance your moving object is mostly around a certain distance, say 2 meter here. So we can simply based on their ratio, and we can estimate the corresponding. For instance, if we can detect there's a zero 0.5 meter movement here, we can estimate that their original movement suppose on the 3D thing supposed to be 1 meter. Yeah, just based on the ratio. However, this is quite restricted because it assumes that most of motion is on the plane, and this plane is also parallel to the, the image plane, right? So uh, it cannot tell a lot of uh, uh, such as the vanishing point or foreshorten or those kind of things. They cannot tell those kind of things. So, but then could be applicable in some cases, such as for instance, if you are playing a game such as the old Wii or PS4 games, for instance, you played in front of 2 meter from your camera. For instance, this is a PS Move PS camera, and you get a PS Move here. This is some light sources here, and for instance, you swing your hand and move. When your camera detect that you move, say 40 millimeter in the screen space, and then can based on the ratio. For instance, this is 100 millimeter, and then can estimate. Okay, perhaps you got 1 meter move in the real 3D scene. But this is kind of simplified and too simplified the thing. So we do not really use this kind of model to estimate some detailed 3D motion. Yeah. And there's also another projection called further simplified called also graphics projection. It actually it ignore the the, the, the foreshortened cases. So it directly project, for instance, get the x direct project to x point. So in this case, based on the pinhole models, their idea is that okay, we have our thing is pretty far from the pinhole, and we have a pretty large pinhole. Yeah. So AV light can go straightforward direct because our angle is pretty narrow. So then can simply use parallel light to represent. Uh, so it means our distance from the pinhole size is the ratio is uh, infinite. So then use this kind of directly take x become the x plane. Yeah. So this called so-called also graphics projection, but it's only applicable to some pretty simple cases. Okay, and so we have shown you the idea of the pinhole model, right? And the perspective, and it can explain uh, a lot of phenomena such as the vanishing point and the foreshortened cases, right? But when 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 you touch your real cases or your iPhone, right, or your Samsung, say what is the newest version, S22 and or 12, I'm not sure what is the exact, and they actually do not really use the pinhole, right? Because they usually have some lens, right? So why do we have to use a lens instead of the pinhole? Uh, and while the pinhole only applicable for such as the camera obscura for such as kids solar uh, eclipse observation. That is for some reason, right? So let's take a look at some example. So if your pinhole is too big, So for instance, this is our camera obscura here. So if your pinhole is too big, so what is pinhole too big mean? For instance, the original pinhole model is assuming there's only a point over there, so your line can go through the can have a single way to pass through the pinhole. Right? But if you enlarge your pinhole size, for the point light here, a point light will spread to different direction, right? So your point will no longer be a point; it will be spread, and multiple ray will pass through your pinhole. So a single point will become a spreaded sphere in your film or CCD, right? So if you have a candle here, say for instance we have let me show you a candle here. We for the this is the another point is in blue, and through the big pinhole you will see it will spread here, and for the green one, let me show another green one. Green point here, through the pinhole you will become a pretty large sphere in your film. So for instance, the correct one figure here is LUZ optica. Okay, so if you use a large pinhole, say the pinhole is in 2 millimeter. 2 millimeter is yeah not that big, but you will get image like this one. Yeah. So when you gradually shrink your pinhole size, it will become clear, right? And when we reach the point, uh, 0.35 millimeter, so that is just a point, you will get a clear image, right? So your pinhole, if is in the right size, image will be sharp, but the problem is that it will be dark. Because you can see that if you have a candle here, your pinhole only allow the single point 0.35. You cannot even draw length with a ruler, right? Yeah, you have to use some pretty tiny pin to poke a hole over there. So there's only a small portion, pretty small, tiny portion of light can pass through the pinhole to reach your camera film. So the image will be dark, and but someone say, oh, if dark is okay, but the pinhole size, uh, even the pinhole size is smaller, it will still have some problem. So what is the problem? So whenever your light, your hole is smaller and reach some uh, smaller than some thresholding, some numbers, you will result in the diffraction effect. Diffraction means 绕射, right? So the wave here will be spread again. Yeah, if your hole is too small, so it will. So in this case, when you further shrink or reduce your pinhole area in size, and you will see that the image will become blur again. So this is problem for a pinhole. You have to carefully design your hole size, and you must have sufficient light. Yeah. So okay, some of students may say, okay, so so pinhole image supposed to be dark and can only capture some light source. So why can we say, for instance, in our a lot of news, right? Then say, okay, someone is captured by some pinhole camera, not pinhole camera, 针孔摄影机, right? In someone is captured by some 针孔摄影机 in English supposed to be the hidden camera. In the motel, for instance, some famous uh, statesman or political guys and was captured or showed video is captured in some motel or somewhere. So if we directly use a pin, if the bad guy really use a pinhole, then actually cannot capture a lot of things unless uh, the the lighting illumination of that room is uh, bright and the, the famous guy or the man be captured is grooming, right, or is shining. They wear some uh, lamps on his body. Yeah. So for most of the real say the hidden camera, then actually still have some lens in front of the pinhole, right, or within the pinhole. Yeah. So let's move forward to the next topic, the camera with lens. So the idea is that if you have a pinhole here, if you would like to make your uh, say your image brighter or can capture more detail of the scene, you have to enlarge your pinhole. Right? However, if you enlarge your pinhole, a single point, for instance, the candle tip, will become a big sphere in your film, on your film, and so every point uh, become larger. So you will when then superimpose together or then blend together, your image will become pretty blurred, right? So for real work, uh, we have to use some camera with lenses. Yeah. Uh, uh, so I think most of you have the idea about Snell's law in high school, right? So when a light goes through some, for instance, pass through some water, right, or glass, right, because their density is different. For instance, this is the air, and when it goes through the water or gas or the glasses, then the medium's density is different, so the line will change their direction, right? This is called a refraction. So, so the benefit of the lens is that if we can carefully design our lens, we can make, for instance, single point P here. We can, through this lens, we can say converge at a certain point. If we can, of course, through the center, we will go past through the center. However, if we going up, then we can use the refraction to change the direction, lighting direction, and make the point. For instance, this ray will be converge at a certain point uh, on the film, right? So that is the first or the most important issue we have to use a lens, because it will make our film or the capture image uh, during the dark scenes, right? Yeah, and so we no longer so in this case we no longer have to wear uh, some light or lamp on our body. We can still capture our body's shape on our camera, because for instance, for a pinhole you can only capture a single ray, right, or a tiny ray, and through the lens you can capture multiple rays and make them uh, converge in certain places. So there's another term called aperture. Aperture means 光圈大小 in Chinese, right? So so when you use your digital camera to capture a scene, especially during after the evening, everything will be dark, so you can turn on or make your aperture larger. Right? Then your camera can receive more light, and you can get more clear image. Yeah. And of course, there are some side effects we will talk about later. And so about the lens, so how can we estimate the corresponding projection through some equation? Yeah. So there's a so-called thin lens model. Uh, this one's supposed to be taught in junior high school or high school. Yeah. So the main idea is that if we have uh, so how to define the thin? So what is the thin or the thick lens? For instance, this one is a thick lens. This one is a thick lens. Let's depend on the ratio. For instance, you have a curvature here, and you have a distance between uh, the curvature of your lens, and for instance, this is a distance, and this is your curvature. Say this is a C here. So depend on ratio. So if your D is pretty smaller than the C, so for instance, this C1, C2 here, and the equation is kind of complex. So I just let you know some idea. Yeah. So if your D is much smaller than the C1 and the C2, then we can call it a thin lens model. Yeah. So the thin lens model is that, for instance, given a light, then pass through the camera center, you can go straightforward, right? However, if there is a parallel line from a distance, then this line will go pass through the so-called focal focus. So this is the common focus we call. And this distance is so-called the focal length. Focal length, right? So you can see that through this light, for instance, this is a parallel light, we can pass through the focal, the focus, right? And this light, this ray can pass through the camera center and go straight forward, and we can find their intersection point here. And again, this is the light can be reversed, right? So the parallel line will go from this point, will go back to P here, right? So through this intersection, we can actually estimate the so where is the focus, right? Oh, sorry, for this is focal point. Yeah, focal point. So we can know that where is the projection point, clear projection point, yeah, of your camera, right? So this is focal point, yeah. And so when you adjust your say your focal length, we actually talk about for a real the thing. Uh, for instance, when you adjust your camera to do the focusing, which means you make your image clear, what we do is actually to either move your lens or your plant, right? There is actually a formulation about the relationship between the so-called Z here. Z prime is in the the within the camera, and we also have F is the say the focal length here, and the focal point is length here, and we can see that okay. So we can through this equation we can whenever you have a Z here, the distance here, negative Z here, you can estimate where can we put our plant or film to make the point converge. So that is why sometimes for instance, when you cap some using some camera to capture something, but some others unfocused point or image will be blurred. That is because let's take a look at this example. If say if this is a candle here, right, and it will be the point will be converged at the P point here. So we supposed to put our CMOS here, right? However, if you do not put on the right direction, say for instance, put in this place, you will see that the P light here, so this is YOP, will become a spreaded sphere. So in an image, it will become from a point P here to a spreaded point here, right? And again, when you move your to this point, after this point, the 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 projected point will be spreaded again because it's no longer convergent and straight extended, right? Yeah. So this is the so-called the Singleness model. Yeah. So based on this idea, actually, when we take some photos, we can actually use this kind of technology to focus on some of our target. For instance, take a look at this figure. So we have multiple uh, stack of cubes here, and uh, and we can actually, based on our model, we have select, for instance, this is the cube one here, cube two here, to here, and we can adjust our focus and, for instance, focus on the C1 here. So this may not be a good one, but check. C1, C2 here. So not a C1 here. C2 is supposed to be here because C2 is far from our lens. And when we do this kind of projection, we'll find C2 will be, for instance, will be converged earlier and then spread again. Okay, something like that. So, and through this idea, we can focus on some of our targets. So this kind of, for instance, in our such as 人像模式, or some use, if you would like to use some high-end camera to capture some your girlfriend or boyfriend, you can make your focus on he or her, on him or her, and perhaps you can use this kind of idea. And so, for instance, there are a lot of beauty here, and you can focus only on your girlfriend, and for other beauty, you can, it will become blurred, right? And so that is so we usually call this kind of thing the depth of field, because for a real lens camera, uh, we we only have a short distance. For instance, this is the short distance here. The image will become clear. Otherwise, uh, for instance, during this distance, your image will become clear. Otherwise, closer or far from this range, the image will become blurred. Right? And there are also some way to make the this kind of range say larger. One of idea is that, say, we can shrink. So this is just appendix. If you have no idea about the camera or depth of field, you don't have to worry about that. Okay. So one trick to avoid this kind of thing is that perhaps we can shrink our aperture. Aperture means 光圈. Yeah. Whenever we shrink our capture, we can reduce a lot of, say, the uh, the ray uh, to the border of the lens here, and then we can, through this kind of idea, we can reduce the spreaded sphere. Okay, so we can make our images slightly clear. And but this depends on your requirements. So someone like this kind of effect. So whenever you take a lot of, such as the flower, and so, or some beauty, or some muscle guide, if you want to focus and make your background or others blur, you can choose using a large aperture, right? And on the other hand, if you hope that you can capture things, most of them are clear and not so blurred, and you can choose a smaller aperture. Yeah. So this is just an appendix. Yeah. And for real cases, yeah, for about the real camera, for the real things, we actually do not really have uh, thin lens because we usually have some, uh, say, certain of width of your lens, right? So, but we can use some approximation for this kind of situation. For instance, for real light source for this thick lens, we can say this is a thick lens. Your light actually goes through this way and refracted to this way, right? And it actually direction is this way. So the red is the real lens, but we usually can extend uh, the sixth lens through the thin lens model. The idea is that perhaps we can use assume that there is a pseudo, say the principal point here, and with this principle we can regard them as a virtual space or something. So we can extend the parallels along this space after the principal point, and then can refract it to through the focal point after the second principal plane. So this is just a way to simplify the, uh, the analysis, but the real line is goes through this way, the red one. But we can analyze using the blue instead. Okay. And through this analysis, for instance, for light pass through the edge point, it will go straight forward to this direction and then reflect it again. So it's just like a thin lens, and then we can put intermediate glasses within it. Yeah. So this is a thin lens, the real cases. Yeah. And however, for the real, uh, for instance, the cell phone camera you use or the Sony or Canon camera you use actually composed by multiple, say, multiple lenses. And in our overview, have shown that, for instance, in your iPhone 13, say in your iPhone 13, you actually have more than say 8 and more lenses for your camera. Yeah. So they have to adjust the light direction to make them project on your CCD, CMOS, just within a short distance. Yeah. And there also have some so-called the aberration of your lens. Even though we say okay, the lens model have some benefits, such as we can included more lines and make our image brighter, and we can capture image uh, for the dark environment, right? However, we have still have some real problems, such as spherical aberration. Spherical aberration means, for instance, when you have a large lens here, right, and we hope that they can follow our way to converge at a certain point, but sometimes for the uh, rate at the border of your lens, then will say converge earlier, or they have a larger and they have the shorter focal length here. And so in this case, your image will become blurred again, right? So this sometimes occurred such as for instance, the Hubbard telescope, then for the first step, launch on the for their first version on the space, then encounter this kind of problem. Yeah. And in addition to physical aberration, they are also so-called chromatic aberration. That means if you would like to bend your light through the lens, right, and through the refraction, actually different kind of wavelengths of ray will have different kind of uh, refraction angle. Right? So if you have so whenever you would like to capture an image with RGB, say CCD here, and your image will slightly blurred, right? Because uh, uh, so, because just like the in Chinese this is called 三棱镜, right? For instance, if you have a large refraction here, then different wavelengths will have different uh, direction. Yeah, so it will make your image blur because their 3 rate will not be pass through the same CCD location. Yeah, so for real cases, we usually have to use the compound lenses. For instance, use the multiple lens to compound means 复合, right? So you have to use the compound lenses, carefully design those lenses and try to minimize those aberrations. And however, for the compound lens, there are some problem. The problem is usually called the netting effect. I'm not sure whether my pronunciation is correct because it's sort of from the French, right? French word. Yeah. So the netting effect means because you use the compound lens, the original light pass through, say, the first few lenses, the line will no longer be passed through the other lenses. Therefore, some of the image, say, for instance, here's a tree here, and then here's the projected tree here. All the trees at the border of your, say, uh, your lens or your scope, then will become the brightness will be dropped significantly because a large portion of them is uh, did not capture by the following lens. Yeah. And so for our human eye, and for our human eye, actually, it's also a lens here. And so for instance, you can see that this is our human eyes. So for our human eyes, we actually have the 2 main lens uh, uh, for our camera eye system. The first one is our ray will first bend it, or you can say refract it at our at least around our not the iris here, around the cornea, right? The 角膜. And then this is the first refraction, and then it will go to our second lens. This means the 水晶体 here, and then we will converge to our or focus or be intersected on our retina. Right? So we can say a large portion of refraction is on our cornea, or I have to check its pronunciation. And so then the line will be adjusted by our the following lens. Yeah, this is our 水晶体, and then focus on our the retina. Yeah. So you can say this is kind of our film or CCD, and we have compound lenses model with first main lens, and this is our second lens. Yeah. And so for real world, what we use is actually the lens model. However, we still use the pinhole model. So idea is that for lens model, we actually will encounter a lot of problems, such as the geometry distortion we'll talk about later. Yeah. For instance, for box here, during our using our lens, it can be such as spherical or radial distorted, means it will extract it to certain sizes. Yeah. And then there's also some geometry distortion. Yeah. And there are also some blur problem, because if you would not focus on some object, it will be blurred, right? And but we still use the pinhole model, because we after the say chapter 4 or 5, you will learn that, and we usually use pinhole model to represent the 3D to 2D cases. And for those distortion or blur, we can use some additional procedure to compensate or mimic those effects. So we usually use say the pinhole plus say the radial distortion model or some other model to compensate those effects. So we can still use a pinhole model. And because it's quite simple, and the pinhole model have we it can the formulation of pinhole model is mainly based on we can uh, estimate them, or we can uh, formula formulate them through some metrics. So we can turn a lot of problem into combined with some other linear operation. So it can help us solve a lot of problems through some linear equation, because a lot of distortion then are actually non-linear. And uh, if you would like to deal with some nonlinear thing, then the formulation will be slightly difficult. So in our say chapter 6 to 8, we'll talk about such as stereo and other things. We still mainly use the pinhole model to such as a reprojection or something to estimate the relationship between 2D and 3D. And for those distortion result from lens, we can use some other model to compensate the effect. Okay. So that is the second class to date. Yeah. So let me stop the video recording here. Oh. Okay, so this is the second class today, and actually I will go into the third class after a short break. So you don't really have to follow or go with me, because I will put the recording online. That is the third hours. So if you would like to stay, you can stay and listen to the third hour this week. If not, you can leave and you can see the video recording. And so if you have any question, perhaps let me take a short break. And if you have question, you can ask, ask me. Okay, perhaps you can ask a question first. Yeah. I wonder whether there are questions about the course content. You can ask first, and then we can take a short break. Okay, so someone asked a question whether we have less weeks recording. Actually, we have, and we also have Google Drive for Land, and we will announce the link after we upload today's recording. Yeah. And by the way, for a question, you actually can use the you use you can uh, speak about your question through the WebEx. Yeah. You can simply turn on your camera. Yeah. Camera. Sorry, microphone. Okay. If there's no question now, then perhaps let me take a 10 minutes break and then we'll go to the 3 hours. But you don't have to follow me because I will upload the video as long as they are correctly recorded. Yeah. Okay, so let's move to our third uh, hours or third class, but we actually only took about say 40 minutes around. Okay, so if for student, if you have some other event such as if you some other course, you don't have to worry about you will get some punishment or if you leave this one. But because the third hours, the mysterious third hour is officially is a synchronous video, but I think if we would like to do that, we still have to record. So you're welcome to stay here and listen to the third class. Okay. Okay, so I will start recording. And you find anything wrong, such as do not have voice or do not see the share screen, uh, try anything to let me know. Okay. Okay, so let's move to our second part, so-called illumination. Illumination is actually regarding to the lighting effect. Yeah. So why do we have to talk about illumination? Because for a 3D thing, we have there are two main things. The first one is geometry, and for geometry, we can use some pinhole or other camera model. And for the second one is about the illumination, lighting. So this part is sort of overlapped with the computer graphics, the rendering or shading chapter. So if you are familiar with this part, you can skip the first half of this part. But first of all, we will introduce such as some reflection models, such as the foam model, and such as the Lambert abrasion surface actually just the diffuse part of the foam model. And however, I think the most important issue is this one. Yeah, this is supposed to be new for students who have learned graphics. And so this is supposed to be our homework number one. And we will try to use the reverse of those foam or conversion model to try to reconstruct the surface, such as uh, a few years ago we reconstruct such as a bunny or something like that. Yeah, bunny. Okay, and or some statue. Yeah, I remember there's a statue, the Greek style statue. Yeah, it is. There's few years more number one, but I'm not sure whether today we can reach land. But let me try. Okay. Okay, so again, we will have some sources from uh, the textbook and some related lecture notes. So the first part, illumination, is actually mainly discussed in the graphics field. Yeah, but so we say that graphics and vision sometimes some concept can be we can communicate with each other, right? So if you would like to say the lighting the or illuminate the real thing, such as the I guess most of you have known that this is a corner of our library sixth floor, and this is supposed to be our library second floor. The main hall is actually second floor. Okay. So if you would like to see this kind of thing, then actually result from so-called refraction. For instance, if you are eye here or your camera is here, so where is those light from? There are only a few illuminate, so-called self-emitted light, such as the lamp here or the uh, uh, fluorescent fluorescent lights, but most of the thing we see is actually through the reflection. The light goes through some surface, and the surface refract. Refract here means the 反射, right? From the surface to our camera. Okay, so we usually have to encounter uh, two kind of property. The first one is your light source. It depends on your light source spectrum, such as red, blue, green, right? And also regarding some geometry, right? Such as if you have different kind of uh, lamp uh, or, uh, or light, and sometimes we also have to encounter so-called directional and attenuation. Means your line will gradually reduce, your intensity will gradually reduce when you uh, have a long distance from your light source. And for object, we also have this kind of property. The first one is different kind of object, such as this is a gray pole here, and gray pole here, and so it's actually when a white light emitted on the or sprayed on the surface, and most of the light or a portion of light is absorbed, and a large portion of them or a portion of them are reflected. So therefore, we can see a gray light or a gray intensity at this region. That is because the light absorbed and partially reflected. Okay, so the reflected light is related to the object's geometry, such as if you have different location, orientation, and microstructure, and all of them will influence your light refraction. Yeah. And so because it's not graphics course, we will go through this part faster. So for instance, if you have light, so what is the light's uh, pathways to your eye or to the scene? For instance, given sunlight, it will spread a lot of ray actually, and then spread infinity number of rays, and perhaps one of ray will reach some surface, right, or plane. So we can say there is a B here, and it will be scattered to multiple directions. Actually, then because we are in the uh, analog world, so actually there are infinity number of rays. Yeah, but in computer science, we usually use a limited ray to simulate this kind of situation. So when a light uh, emits or cast on the surface, which means the surface, uh, part of length. So for instance, this is 100% of light, and so this is surface, and perhaps depend on the different kind of material. For instance, 80% of the light is absorbed, and 20% are sprayed, are reflected. And the sprayed, the portion or the direction of the reflected also depend on the material. Some of material is easier to spread or scatter the light, and some others is mainly the reflected light is mainly on its so-called a refracted direction. For instance, in Chinese, that is called mirror or 近色, right? Mirror refracted ray. And so in the later course, we will use some simple model to approximate or mimic this kind of refraction, and formulate length into some equation, and for us to solve. Yeah. And before we talk about the equation, let's talk about the real or nature's phenomena. So for light spread from the source, it actually have to go to multiple direction. And the first kind of situation is that light there is a ray and go directly to your eye or your camera. Right. And the second situation is, for instance, the light could be go through some surface, such as these cylinders, and then can reflect it to your eye. So this is the second situation. And in addition to this one, we also have, say, multi-refraction, such as if we have a light here, you could reflect it to point here and reflected point here, and then can cause multiple refraction. Yeah. And so for instance, this is the third situation. And sometimes, if depend on your material, for instance, your light can go through some transparent or translucent object, such as a glass bowl here. And in this case, your light will partially be reflected and partially be so-called transmitted across the, the glass bowl. Yeah. So this is the say the fifth situation. Yeah. So in graphics, we usually call this a global effect, which means for a single light point, light source, it will relate it to all of say all of the object will be involved in the interrefraction. Yeah, but you can see that if we have to uh, mimic this kind of problem, it will quite difficult or quite complex. So this kind of computation we usually use in such as movie or some special effect movie or some 3D animation such as Pixar or Disney did. Yeah. And so we have to focus on our reflection on only a few light. So we mainly focus on these two kind of situation. First one and the second one. So why do we focus on this? Why can we focus on these two kind of situation? Because whenever a light reach a surface, a portion, say the alpha percent, is reflected. Yeah, and product alpha we say 50%. Yeah, it's just a fake number. Okay, and when you for instance 100% will go here, and after reflection only 50%. When it reach another surface, say this one is more absorb more color, perhaps 80% is absorbed, and so only 20% is reflect. So afterward, only 10% of the light is reflected. So when the light reach your eye or reach your camera, only 10% reach your eye. So which means most of these multiple reflected light, the case of 4 or 5 compared with the 1 and 2, the ratio is relatively low. So when we do some computer vision estimation or some real-time graphics estimation, we usually focus on the first two kind of situation. Here it just show you some example of this is actually a graphics algorithm called radiosity, which means we can illuminate the whole scene through some patches heat change. Yeah. Anyway, you don't have to know the detail, but you can see that the light emits sunlight and reflected to some surface. Right? When sunlight emits to surface and then reflected to the, the the wall, and the wall can do some further refraction, and afterward our room will become brighter and more similar to our real cases, right? But actually, the radiosity method is estimated through some solve some equation. Yeah, and in addition to actually for real world, it's actually more complex. So For instance, for light here, let me show you a figure here. This is just a appendix. Okay, it's not. You don't really have to learn the detail. For light here, go through a surface point. For instance, this is say a wood here or a certain metal. When light go here, and this is the reflected light, actually different orientation. For instance, if we have a wood here, we can put it on the uh, on this rotated plate, and when we emit light, we capture how then reflected. Sometimes we can find that different incident angle, which means this incident rate, input rate, and we will have different kind of refractive ratio. So for the real cases, the refractive ratio, for instance, the observation of 50%, actually this property is actually varied according to the incidence and the refracted uh, angles. Yeah. And so that means just that you know there for real work cases is more complicated. However, for computer graphics, real-time computer graphics, or the computer vision, we actually can use a simplified model called the local model. Just I have mentioned that perhaps we only have to worry about, for instance, the direct light and the say the the, the reflected light of just a single refraction. Yeah. So for instance, this is called a multiple reflection. This is called a single reflection. We only have to worry about the single refraction light and the direct light source. Yeah. So we usually call this a local lighting model. Yeah. So there are some different light sources and about the refraction. So one of the most common use is the point light source, which means you have a point here. You have uh, this point can provide some light to different location, multiple locations here. And so this one is most popular used in graphics. But for vision, computer vision, we usually use the distant light source, which means for surface we only have a single direction, which means all of light is can be simplified by a single vector here. For instance, here we have L1, L2, L3, L4 here, but for computer vision, our main idea is to reconstruct the surface, right? So we can simplify the the light definitions. And there are also some other light, but we do not really use them. For spotlight means, for instance, you have a cone here and restrict the point light source region, but we not really use them in computer vision. And for ambient light, which means because for real world we have sunlight can be reflected to there are a lot of different kind of refraction or third or fourth or multiple refraction. We still have to use some constant or some number to refract or to represent this kind of refraction. So this called so-called ambient light. We'll see that later. Yeah. And for light source, there are two. Most of the material, refraction material, actually is between the smooth and roof surface. So what is the roof surface here? Roof surface means light here goes through a surface. It will reflect it to all different kind of all directions. So this is called a perfect roof surface. And for line surface called the smooth surface, perfect smooth surface means line goes to the surface point and will just go to the reflected ray direction. So for instance, the theta will be equal. Yeah. So most of the material is between the perfect smooth and the perfect. So we usually call this one is diffuse surface, and this is one is speckle. So most of material is somewhere between the perfect specular and perfect diffuse. Yeah. So there is a famous model called the foam model. Let me so 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 the model we will talk about later is actually derived from some observation. So when scientists of using such as the BRDF device, we have shown you that. For instance, we can use a surface here, some light source. We can use a camera and put some different kind of direction to estimate their reflection. We find that we can our light source will sort of like this. For instance, the light source here, and our refractions, the ratio of refraction will be sort of like this kind of model. So what is the meaningful for that? So this kind of shape can be decomposed of, let's say, uh, ellipse plus dome here. So it will become something like this one. So so this one is, let me use another color. So this is light source. This is the perfect refraction direction. So you can see that most of light is reflected in a certain reflection direction. Right? So this, and other lights can also be reflected to other orientation or direction. So so the uh, scientists observed that perhaps we can use a combination model to say mimic or the model the real world reflection, simplify their representation. Yeah. So the phone model we talk about later is actually derived from this kind of idea. So this kind of ray is actually from the perfect speculum, because it's mainly reflected at the perfect reflection direction. And this kind of dome shape is actually a reflection for uh, all direction. So this actually derived from the perfect diffuse. So so in the model we talk about later, we will use the combination of the perfect specular and the perfect diffuse to form this kind of the common reflection for different kind of materials. Yeah, and so there are some second some notation here or some symbol here. Yeah. So we usually use the arrow for the light source, and we use surface normal. So this is the surface. We have a surface normal n here, and we have a perfect refraction rate here, r here, and so theta here is identical, and we can simply use this equation to estimate the r. R, you can see that, for instance, if we have the, so how can we derive this one is because r, the arrow, their means or their uh, average of them is actually this point. This point is n dot arrow n. So this is the projection. This ratio is n dot arrow, and this direction is n. Okay. So as long as we have n and arrow, the we can get the r here through this simple equation. And so based on this kind of uh, vector, we can derive our the phone reflection model. and this is commonly used in graphics course. Yeah. And so for the first part is called the ambient light. Ambient light is actually just compensation, or you can say the approximation for those multi-refraction light. Yeah. So so for instance, if what it look like if we have a sphere like this one is because it's trying to mimic or simulate the refraction from multiple rays. They are from all of the direction. So this formulation is do not have any orientation. So it's just a simple color over here. So there's no vector here, no color vector here. So for instance, if we have so the K here is a reflection, so-called the ratio. We usually call uh, the ambient reflection coefficient. For instance, it's just like 30% here. Usually use for 0.3. For instance, when light 100% called 1 and reflection 0.3, we can make them become 0.3. And we can do that for 3 color channel. For instance, we can use ambient for R, ambient for G, ambient for B. Each of them have their individual uh, reflection coefficient. For instance, we have color 111 here, and this one is a Blu-ray blue color. So for the R means red is reflection of probably only 10%. One. And for green one is also perhaps only have 10%, so result is 0.1. And for the blue, because it's you see the blue means a large portion of the Blu-ray is reflected, so the reflection one is say 0.4. So you got the color 0.4 here. Yeah. So this is the color R and G and B here. So this one is can be manually adjust, or it can estimate through some. For instance, you can take some camera and reversely estimate these coefficients. Okay. So this is the first kind of light, the most simple one called the ambient light. So there's no direction. And the second one is more important, or it is actually the most important reflection for computer vision, called the diffuse. Yeah, because so what is the diffuse light try to simulate? So its idea is that, for instance, if you have a perfect roof surface, if for layer even though you look like they look like smooth, such as the blackboard Chinese is 黑板. Yeah. Even though their color, you can see they look like smooth, but their microstructure is actually quite roughy, and there are some tiny plant over there. So whenever a light reach the surface, it will be reflected to all of the directions, all possible directions. But why do we say this is the most important uh, reflection part for computer vision? Because let me erase the stroke. The most important things is that there is a property called Lambertian. The cosine law is that, for instance, if your line is go directly through the top here, it will go to all, even though they can go to all the direction. However, when you tilt your light, say for instance, use the blue color right here, the reflection, even though it's go to all direction, but the reflection light will become darker, or the intensity will be not that much. So that is because, for instance, let's take a look at the example here. So for for instance, this is a one unit line here. So this is their intersection here. When they go to this surface point, it's 100% provided to this point. However, if you tilt your line here, 1 unit here, your intersection will become larger. Yeah, it become cosine theta. See? This is when it will become larger. Yeah. So because the intensity per unit have to be enlarged, will be spread to the region of reciprocal of cosine theta. Yeah. So your reflected light will be reduced. So that is quite. If your light is just on the top of the surface, it will spread. It will have a larger or stronger reflection here to all directions. But when you tilt your light and gradually make them move down the light, you will see that the light will become reflected light will become say relatively uh, weak, or you can say the intensity will become uh, lower or reduced. Yeah. So there is important formulations here. So again, we have a reflection coefficient. It depends on your material and the color, reflected color. And this is also the light source. For instance, we can say it's 1 or 0.5 or some others. And this important component here is n dot L. N dot L means the angle between the light and the normal. If they are paralleled, you got 1 here. If you got, say, n and L here, theta, n dot L is actually cosine theta here. Yeah. So based on this equation, we can model this kind of phenomena. Yeah. So this kind of phenomena means if you have upright light here, you will have stronger reflection, and if you have larger angles and oblique light, and your reflection will be smaller. And so why is it most important featured or reflection for computer vision? That is because, let me draw a figure here. If your light source is here, you can see that the surface normal is in this direction, uh, is nearly parallel to the light source, so it will be bright. And when you gradually change your normal, for instance, normal here is in this direction, the reflection will be smaller, right, or weaker. And when you go this direction, you can see that almost the surface is dark. For instance, the reflection is 0.7 here, and here it will become 0, right? So you can see that given a simple light source here, and your refraction or your image, result image, is related to your surface normal. So based on this kind of image, we can actually derive, or you can estimate the surface normal from a single image, or of course we can also use a multiple image. So so this is the most important refraction component. So we may use them for our say the homework number 1. Yeah. And so there's the last component. The last component called the specular coefficient, or the specular refraction. So where can we find a specular coefficient? For instance, when you see this apple here, most of refraction is result from diffuse. However, you can see some white spot, white band. They are actually from refraction. So, for instance, when you see some comic they usually have some this kind of shape, right? So those reflection actually from some lamp on the top of the room, and so the specular actually try to uh, uh, mimic or try to approximate the so-called perfect specular reflection here. So, for instance, given this kind of shape model we have shown you, the specular only uh, occupy those regions. Specular reflection only occurred at those regions. For other region, there are actually no contribution. So when we estimate the surface, we usually, because then the specular only occupy a few quite few uh, regions, so we mainly use the diffuse for surface reconstruction from image. Yeah, if we would like to use photometric stereo. And before we let me finish these slides, and then we can finish the class today. So how can we model this kind of reflection? So our idea is that if we have a line here, we have a reflection here. Yeah, perfect reflection. However, there are actually no perfect reflections, perfect specular refraction material. So your line will still be spreaded to other direction, but not too far from the perfect reflective ray. So the idea is that perhaps we can simply use a model just like the cosine model we mentioned about. Right? So we can use a cosine model here. It uh, can represent the degrade or the reduction or the degeneration of the not degeneration, the faint out of the light, the faint out situation of light. When the light is 100 is most bright points here, and it will gradually faint out and become more or non-visible, right? So idea is similar. We still have coefficient here to control the reflections. So we can use different kind of ratio to control the R and G and B. And this is also, for instance, we can put one here to for light, and here we can put the cosine function here. And we try to simulate, for instance, perfect refraction here. And if you have your whenever your angle reflection angle is here is so-called phi. Phi will whenever the phi is larger, the reflection rate will be reduced. Yeah. So for instance, if you are on the R, you will have the perfect, not a perfect, you have the largest specular reflection, but it will gradually uh, uh, fan out speed will be increased if you improve there is a, exponent here. So for instance, the equation is cosine of phi here, and if you increase your alpha rate will become refractive rate will become more narrow. So usually it's the for we can say if your alpha is close to 5 to 10, it will look like plastic. However, if it is larger, say your alpha is 100 to 200, it will can represent to some metals such as uh, the stainless uh, iron or some others, right? Okay, so uh, so in the end, we actually have to combine all of these kind of street light to represent the refraction of a scene. But we will talk about then in the last course, and then probably talk about this photometric stereo in the next course. Okay, so that is all I want to introduce. So let me start recording. Yeah. So if you have any question, you can stay here and discuss with me. Otherwise, we dismiss our class.